Finishing up chapter 4, remember in part A we talked about compounds that were held together by ionic bonds, and we call those ionic compounds. And last video we talked about compounds that were held together by covalent bonds, and those are either called covalent compounds or molecules. So that's the category we're still in. So we talked about learning how to tell me the Vesper geometry, the molecular shape, and the bond angle. Today we're moving on to where you're going to still be using the Lewis structures to tell me the polarity of the molecule, whether the molecule is polar or not polar. So before we get into that, I need to teach you a little bit about electronegativity. So here's a reminder: covalent bonds occur when elements share electrons. So remember, when you see a line drawn between two elements, that's two electrons being shared. And once again, remember that Lewis structures are formed by giving all the elements their octet. And so if we count up around chlorine here, chlorine is feeling 8 electrons, 2, 4, 6, and that chlorine fills these two that are being shared, so that's 8. And as a reminder, hydrogen's the exception to the octet rule, hydrogen and helium, and their octet is 2 electrons, and this hydrogen right here is feeling 2 electrons, so it's 2 being shared. All right, so elements don't share the electrons equally or evenly. So these 2 electrons might not be shared, right there in the center of the hydrogen and the chlorine. They sometimes will shift closer to one element than the other. The definition of electronegativity is it is the measure of the attraction that an atom has for the electrons in the bond. And here is a periodic table that is giving the electronegativities of some of the elements. You may have to refer to this table in your book to answer some of your homework questions. But I want you to see the trend. It turns out that the electronegativity of the elements decreases as you move down a family and increases as you move to the right. So this is the same trend that we saw with the atomic radius and also the ionization energy. Atomic radii, they get smaller as you move down and smaller as you move to the right. The ionization energy gets bigger as you move down, and no, wait, I said that wrong. The ionization energy gets less as you move down but bigger as you get to the right. So remember, I don't remember if you remember, but I had told you that I didn't particularly like this trend where you do down and across, because then you have to remember that they're doing opposite things. So let me grab my pen real quick and I'll just refresh you. I like to do the trend where I say as you move to the right and as you move up, because then I can keep everything the same. Where I can say, as I do that trend, the radius of the atoms decreases, the ionization energy is going to increase as you do this trend. So fluorine is the most has one of the highest ionization energies, and now we can use this for the electronegativity. So electronegativity is going to increase with this trend. So that's kind of how I have it memorized. Another way to do it is just with this trend, just remember that over here in the upper right hand corner of the periodic table, so I like to just kind of focus on fluorine, that's where you're going to find your smallest atoms, those with the highest ionization energy and those with the highest electronegativity. If you go down here to the bottom left, you get your biggest atoms, lowest ionization energy, and lowest electron negativity. Okay, the electronegativity and polar bonds. So elements with larger electronegativity values have stronger attractions for those shared electrons. So in general, metals are going to have low ionization or electronegativities, and your nonmetals are going to have the high. Going back over here to the table, I didn't spend much time looking at the numbers, but if you notice, fluorine has a 4, an electronegativity of 4, which is the largest. So that means that when fluorine is in a bond and it's sharing 2 electrons with another atom, it is going to pull those 2 electrons closer to itself. So the larger the electronegativity number is, the stronger that pull, the stronger the attraction for those shared electrons. So since bonding electrons may not be evenly shared, the possibility of polar bonds exist. So a polar covalent bond is one with a positive and a negative end. Okay, so here's an example focusing on hydrogen chloride. I've got the electronegativity values here. So like I said, the larger the electronegativity value, the stronger the pull. So since chlorine has a larger electronegativity than hydrogen, these two electrons that are being shared are actually going to shift to the right, and they're going to be found closer to the chlorine. So negative electrons closer to the more electronegative atom leads to a polar bond, which is sometimes called a dipole. So there's two different ways that a chemist is going to show a reader that there's a polar bond. One is using this, what we call a partial negative and a partial positive. It's using the lowercase delta Greek letter. When you go to draw this, it's just like doing a figure 8, but you stop, you don't complete the 8. So you put the partial negative sign by the element with the larger electronegativity value, because that is where the electrons have shifted. And if the electrons move away from the hydrogen, then that's going to leave the hydrogen side more positive. So that's why it gets the partial positive symbol. Another way, instead of using this partial positive and partial negative symbol, a chemist might use this arrow, where they always point the arrow to the more electronegative atom, and then they do a little plus sign on the end of the arrow by the atom that is more positive. A polar covalent bond occurs between nonmetal atoms. Well, that's a little redundant. I'm hoping you can see why, because covalent bonds happen between nonmetals. So remember, ionic bonds happen between a metal and a nonmetal. Covalent bonds happen between two nonmetals. So a polar covalent bond is one that occurs between nonmetals, and it is an unequal sharing of electrons. Okay, because when you have an unequal sharing, that's when the electrons shift, so you have a positive and a negative end, and that's our definition of something that's polar. Polar covalent bonds have a moderate electronegativity difference. So when you do the subtraction, so remember from math, when it's asking for a difference, it wants you to subtract. So when you take the two atoms you're looking at and you subtract them, if the difference is 0.5 up to 1.7, then we call it a polar covalent bond. So here are some examples. If you have a bond between oxygen and chlorine, you look up the electronegativity values. I do not expect you to have those memorized. So for test purposes, I will always give you the electronegativity values. But you need to know, if I'm asking you, is it a non-polar covalent bond or a polar covalent bond or an ionic bond, your brain needs to say, oh, I need to get the electronegativity values and do a subtraction. And then look at the difference. So oxygen and chlorine, when you do a subtraction, is 0.5. So if it's 0.5, and if it includes those ends, 0.5 and then 1.7 and anything in between, that's actually kind of an ambiguous, it's not as set in stone like that in chemistry, but for the sake of testing, I'm going to just, have it easy for you guys to memorize. So if it's 0.5 or 1.7 and anything in between that, you're going to say that it's a polar covalent bond. Non-polar covalent bond, okay, once again, it's going to occur between nonmetals because it's covalent. It is going to be an equal or almost equal sharing of the electrons. So basically, if you do your subtraction, if you take the difference between the two electronegativity values and it's anywhere from 0 up to 0.4, you're going to say that it is non-polar covalent. And here's an example. Well, if ever it's the same atom, like nitrogen to nitrogen, then it's going to be a no-brainer. You don't even need to go look up the electronegativity values because they're going to have the same number, so the difference is going to be 0. The one that I really want to stress, you're going to hear me stress it often in this class, is the carbon and the hydrogen. Because when we get into organic chemistry, a lot of the organic molecules have a lot of carbons and hydrogens. So, and we're going to deal a lot with the polarity of those organic molecules. So it's good to just really kind of get it in your mind now that a carbon and a hydrogen bond, the electronegativity difference is so small that basically it's considered a non-polar bond. We just, we consider that the electrons haven't shifted anywhere. There's not a positive end and a negative end. So here's a picture that I pulled from your book, kind of showing those different cutoffs. This is called an electron distribution map, where it's kind of showing the clouds of where the probability of finding an electron is. So if we look at this first one here, notice that the electron cloud, this purple region, is symmetrical, meaning the electrons are distributed nice and evenly across the molecule. Okay, so that's what we would call it, a non-polar when the electrons haven't shifted. If we look at this diagram here in the middle, notice the electron cloud has shifted over to the right, meaning I've got more electrons over here, which is why they're showing this partial negative symbol to the right. And then since the electrons have moved away from this atom, we're left with the partial positive. And if we look at our scale, they're saying anywhere between 0 to 0.4 ends up being the nonpolar covalent. Anywhere from 0.4 all the way up to 1.7 is polar covalent. And then if you get to be 1.8, and remember we're talking about the difference in electronegativities. After you've done the subtraction, that number you get is what you're kind of focusing on here on this number line. After you do the subtraction, and if you get 1.8 difference or greater, then we consider that an ionic bond. It is such a difference in electronegativity that the electron is actually going to be transferred. So a quick little summary. So that's the polarity of the bonds. I want to stress here that what we're talking about is the polarity of the bonds, not the polarity of the molecule. Okay, that's going to be coming up here in a second. So if I ask you on a test, are the bonds polar? I want your mind to think about, I need to get the electronegativity values, I need to do the subtraction, and I need to compare it to the 0 to 0.4, 0.5 to 1.7, and then 1.8 or larger. Okay, that's to determine if the bonds are polar. So if it's a metal and a non-metal, the electronegativity difference is going to be very large. That's going to lead us to an ionic bond. If we're talking about a non-metal to a non-metal, then the differences are smaller. If it's a small difference, it's a polar covalent, and if it's a very small difference, 0 to 0.4, then it's a non-polar covalent bond. So a polarity occurs due to the imbalance of charge. This is kind of a summary here. A hydrogen-hydrogen bonds are considered nonpolar because the electrons are equally shared. Okay, I can't stress that enough. Nonpolar, the electrons are equally shared. If we looked at a carbon-oxygen bond, that's going to end up becoming polar because the electrons are unequally shared. So that's going to lead to what we call an imbalance of charge. The charge is going to shift, and where one end is going to become partially positive and the other end is going to be partially negative. Okay, now we're about to switch gears. We're about to move from talking about if the bonds are polar to if the molecule is polar. So chemical bonds may be nonpolar, polar, or ionic. We just talked about that. So this is the bonds, and you can get either a nonpolar covalent, polar covalent, or ionic. But what about the molecule that contains those bonds? So if I focus on water here, and I asked you, are these bonds polar? You would go look up the electronegativity difference and you would find out that they have a polar bond. So I'm telling you that right now, that these bonds in water are polar. The electrons have shifted, and oxygen has the larger electronegativity values, so these electrons have shifted closer to the oxygen. Okay. Now, after you've decided if the electrons have shifted in the bonds, you then have to think about, is the molecule polar? And it turns out with water, the water molecule is also polar. So we have polar bonds and we have a polar molecule. Okay. For test purposes, if I ask you, about the polarity, you need to read it very carefully. Okay. If I ask you about bonds being polar, you're going to get the electronegativities. If I ask you if the molecule is polar, you have to look at the Lewis dot structure that I'll usually provide for you. Okay, so how are you going to determine polarity of the molecule? So if it's a non-polar molecule, if there are only two atoms, okay, so we've got two different scenarios here. Molecules that contain just two atoms and molecules where there's a central atom. And your mind kind of has to think about those two a little differently. If there's only two atoms, the molecule is going to be nonpolar if it contains nonpolar bonds. So if the bonds do not shift, if the electrons do not shift in the bond, then the molecule is going to be nonpolar. If the electrons shift, then the molecule is going to be polar. So basically, if you only have two atoms, then the polarity of the bond is also going to equal the polarity of the molecule. Now, if there are more than two atoms, then the molecule is nonpolar if it has a symmetrical arrangement of the polar bonds. So it turns out that you can have polar bonds in a molecule, but then the molecule itself is nonpolar. And it kind of gets into some summing up of vectors, which we're not going to get into, but this is let's look at carbon dioxide here. If I asked you if the bonds were polar, and you looked up the electronegativity values and you did a subtraction, you would figure out that yes, the bonds are polar. That oxygen is more electronegative than the carbon, so it is pulling the electrons away from carbon closer to the oxygen. But the same thing's happening with this other oxygen. And they're pulling with the same strength because both the oxygens have the same electronegativity value. So it turns out that these two vectors here are going to cancel each other. The two dipoles will cancel. So if you have symmetrical dipoles, then they'll cancel each other out, and you can be left with a nonpolar molecule. It's kind of easy to see when you're looking at a linear molecule that those dipoles will cancel. But it turns out if you have a trigonal planar or tetrahedral, and the surrounding atoms have the same electronegativity value, their dipoles will cancel out. So here is carbon tetrachloride, and it turns out that they have polar bonds. So the chlorines are pulling the electrons away from the carbon, but they are pointing to the corners of a tetrahedral. So they their dipoles end up canceling. So carbon tetrachloride is going to be a nonpolar molecule, even though it has polar bonds. Okay, so then switching to polar molecules, they're going to have a separation of positive and negative charge, which we call the dipole, and once again indicated by the partial positive and partial negative, so that there's nothing new there. If it's a polar molecule, then it's going to have a positive side and a negative side. It's going to have dipoles that do not cancel. So some examples of that. Well, once again, if you only have two atoms, you determine if the bond is polar, and it turns out in hydrogen chloride the bond is polar, so then the molecule is polar. Looking at ammonia here, the bonds are polar. The nitrogen is more electronegative than the hydrogen, so the electrons are pulling, the nitrogen is pulling the electrons towards it. And we do not have a vector up here to cancel out these vectors. I'm going to sneeze just a second. Yeah, I think it's passed. So the vectors do not cancel each other out in ammonia. So this is going to lead to a polar molecule. Okay. So to determine if a molecule is polar or not. So first of all, and this is a biggie that I want you to have memorized, because like I said, it's going to come up when we get to organic chemistry and biochemistry. All hydrocarbons. So I haven't defined that yet, but hydrocarbons are molecules that contain only carbon and hydrogen. Okay, hydro meaning hydrogen, carbon meaning carbon. So all hydrocarbons are nonpolar, since all bonds in the molecule are nonpolar. So if I gave you a really big complicated molecule that had a whole bunch of carbons and a whole bunch of hydrogens, you would just instantly look at that and say, oh, that is nonpolar, because all it contains is carbon and hydrogen. If there are only two atoms in the molecule, then you're going to use the electronegativity values to determine if the bond is polar, and if the bond's polar, then you'll say the molecule is polar. And then for molecules with more than two atoms, so this will be a molecule that has a central atom, like we were dealing with when we were doing the Vesper geometry. For those molecules, I'm going to give you the Lewis structure. You're going to determine the electron groups around the central atom. And if those electron groups are identical, so you have a balance of charge, then the molecule is going to be nonpolar. If they're not symmetrical, then it's going to be polar. So here's a couple examples. So identify each of the following molecules as polar or nonpolar and explain. So in this first one, we only have two atoms. So if you have two atoms, you need to look up the electronegativity values. And I wish I had written those down. I don't want to flip back. But it turns out when you look up hydrogens and bromines, I know hydrogen has a 2.1, but I don't have bromine memorized. But when you do the subtraction, it is going to land between 0.7 and 1. Between 1.5 or 0.5 and 1.7. So this has a polar bond, so you are going to say that this is a polar molecule. Polar molecule, because it has polar bonds. Here we have just two bromines together, so I don't even need to go look up the electronegativity values, because I know when I subtract them it's going to be 0. So the bond here is nonpolar, so because of that the molecule is going to be nonpolar. Okay. For C and D, there is more than two atoms, so I have the Lewis structures provided for you. So the way that my mind kind of does it is, if there's a central atom, I like to circle in my mind everything attached to that central atom. So for silicon here in the center, if I circled everything around the silicon, and I asked myself, Is everything inside these circles identical? And the answer is yes. Then that's going to make this a nonpolar molecule because it's symmetrical. You don't have, the charge separation. If I come over here to phosphorus tribromide and I circle everything around the phosphorus, now you got to be careful because this is where students mess up. You have to circle that lone pair electron because it's also around the phosphorus. Are all 4 of these circles containing identical things? And the answer is no, because this lone pair is not identical to the bromines. So because of that, this ends up being a polar molecule. Okay, I want to give you just one more here that's a quick word of warning. If I gave you the Lewis dot structure for sulfur trioxide, and you go to circle the sulfur surrounded just by 3 things, and so if I circle those 3 things and then ask you, are the 3 things identical, I want you to say yes. So even though this oxygen over here that's doubly bonded and only has 2 pairs of non-bonded electrons, where these have 3 pairs of non-bonded electrons, you still want to look at that as being the same. We didn't get into resonance structures in this class, but it turns out that this double bond is actually being shared equally among all the oxygens. So treat your atoms, that have a single, double, or triple bond the same, as long as they're the same atom. You'd want to look at this and say, oh, I've got 3 oxygens, so this right here is nonpolar, because everything I circled is the same. If I gave you, just one more here, if I gave you sulfur dioxide, so here's the Lewis structure for sulfur dioxide, and you circle it and say, okay, there's an oxygen, which is the same as this oxygen, but I have a lone pair. So these 3 things are not identical because of that lone pair electron. So this is a polar molecule. All right. Dipole-dipole attractions and hydrogen bonding. So we are going to kind of switch gears here and talk about attractions that happen between molecules. Up till this point, we've been focused on bonding between atoms. What types of bonds are holding the atoms together in a molecule? Now I'm going to start talking about what kind of attractions happen between 2 molecules that might make molecules stick together. So in covalent compounds, nonmetal bonded to a nonmetal, polar molecules exert attractive forces called dipole-dipole attractions. So in a dipole-dipole attraction, remember when I say the word dipole, that means I have a positive end and a negative end to my molecule. So that molecule is polar. So it should make sense that that's going to want to stick together to another polar molecule. And it's going to do it in such a way that the positive side of this molecule is going to want to stick to the negative side of this molecule because opposites attract. So the dipole-dipole attraction is called a hydrogen bond. When a hydrogen atom attached to a nitrogen, oxygen, or fluorine in a first molecule is attracted to the nitrogen, oxygen, or fluorine in a second molecule. So I know that might sound confusing, so I've got a picture here to kind of show that. Here I'm focusing on water, which is a polar molecule. Let me draw out the Lewis dot structure for you. If I gave you the Lewis dot structure for water, you would, and I asked you, is this a polar or a nonpolar molecule? I would hope you would say it's polar because the 4 things around the oxygen are not identical. Okay, it looks like, I get a lot of people who say water is nonpolar because it looks symmetrical. It looks like this hydrogen, the dipole here is canceling out this dipole. But remember, it's not a linear molecule. Remember, actually, pause the video for a second and see if you can tell me the shape around the shape that a water molecule is in. So we have got 4 electron groups around the oxygen. So the VSEPR geometry is tetrahedral, but we can only see 2 of those atoms. So if you visualize in your head the tetrahedral shape, remember last video I held up for you the shape of a tetrahedral, and then in your mind take off 2 of those atoms. Actually, do I still have? I don't have my tetrahedral molecule. Anyway, this leads us to a molecule that's bent. So you've got 4 things around the oxygen. They are not identical, so this is a polar molecule. So one end is negative and one end is positive. Well, it turns out that my oxygen and is the partially negative side of the water molecule. And the hydrogens have a partially positive. So it's a polar molecule. So it's going to want to be attracted to another water molecule. And this other water molecule is going to rotate itself around to where the partial negative oxygen is going to be close to the partial positive hydrogen. Okay? So this is what we would call a dipole-dipole attraction, because the poles are attracting to each other. But this particular one with water, not only is it a dipole-dipole, but it has a special kind of force called a hydrogen bond, which is stronger than just your typical dipole-dipole forces. So if I ask you on a test, what is your strongest bond, it would be true that water has a dipole-dipole, but I want you to select water has hydrogen bonding. Okay, so make sure you get this second bullet here down really carefully, because hydrogen bonding plays a big role of the interactions that happen in our body. So I want you to be good at identifying hydrogen bonding. Here's another example of a hydrogen bond. So hydrogen fluoride, there's only 2 atoms, so the electronegativity values are very different, which leads to a very strong dipole here. So the fluorine, which is the highest electronegativity value, is going to pull these electrons that are being shared close to it, leading to a partial negative here. So it's going to be attracted to the partial positive in another hydrogen. Okay, so let's go over that. If you ever see a hydrogen directly bonded to an oxygen, a nitrogen, or a fluorine, if anywhere in the molecule you see that bond, then you're going to say that molecule has the ability to hydrogen bond with another molecule that has this criteria being met. Okay, so memorize this right here. That's going to be very important. Okay, so that is a hydrogen bonding. Hydrogen bonds are the strongest force between your molecules. Now, keep in mind I have italicized molecules here because molecules are between nonmetals and nonmetals, your covalent compounds. When we talk about ionic attractions, those are actually the strongest. The cation and the anion sticking together is very strong. Remember, they have high melting and boiling points. So, but if we're talking about just molecules, hydrogen bonding is the strongest attractive force holding those together, and they play a major role in how DNA is shaped. There is another attractive force between molecules that's called dispersion forces. Those are weak attractions that happen between nonpolar molecules. They are caused by the temporary dipoles that develop when molecules bump into each other. So in this particular picture, I'm showing a nonpolar molecule here and another nonpolar molecule. Notice no separation of charge. It's all distributed evenly. But if they bump into each other, the electrons here in this cloud do not want to be around the electrons here. So it's going to cause these electrons to shift, and you end up getting this temporary dipole. And so the molecules end up sticking together, but it's very weak. So your dispersion forces are your weakest attractive forces between molecules. They're weak, but they make it possible for nonpolar molecules to form liquids and solids. So, for example, say like liquid nitrogen. So nitrogen is a nonpolar molecule. Let me go ahead and draw out. Actually, I don't need to, because you would know that if you did the electronegativity values, you're going to end up with electronegativity value difference of 0. So it's going to be a nonpolar molecule. And so 2 nitrogen molecules you might think are not going to be attracted to each other because neither of them are polar, but they end up, when they bump into each other, you get this this induced dipole, which we call a dispersion force, and that makes them stick together. So because of that, you can cool down nitrogen, and nitrogen is a gas. You can cool it down to a temperature where you can actually get those nitrogen molecules to start sticking together, and that's how you can get liquid nitrogen. So you wouldn't be able to get a liquid or a solid if you couldn't get the atoms or molecules to want to stick together. So here's a comparison of bonding and attractive forces, and I do want you to get this memorized. It's going to be important that you not only know your types of interactive forces, but that you can tell me the relative strengths of each of them. So let's go over each one again. The strongest one, so notice my arrow here, that is weakest to strongest. So the strongest, and it has it broken down into 2 different things. Maybe it's not showing it here. Okay, it's not. So we're going to start off with the ionic bonds. And that is the cation to the anion. And then remember you have your covalent bond, which is the sharing of electrons. The in between molecules, so here's the attractive forces between molecules. The strongest between molecules is the hydrogen bonding. The criteria for that is you need a hydrogen bonded to fluorine, oxygen, or nitrogen. The next strongest is our dipole-dipole attraction, and that happens between polar molecules. And then our weakest attractive force is dispersion forces, and that happens between nonpolar molecules. So it's going to be very important if I ask you for the attractive force, the first thing you should do is look to see if it's ionic, because that one's the easiest to spot. If it's a metal bonded to a nonmetal, it's ionic and the force is very strong. Okay, if the molecule has nonmetals in it, then what you need to do is you need to say, I need to decide if this molecule is polar or nonpolar. I need to focus on that central atom, circle everything around it, and decide whether they're identical or different. Okay, assign whether it's polar or nonpolar. If it's polar, then it's going to have a dipole-dipole, and you have to do one more step and say, ooh, is it that special kind of dipole-dipole where I have a hydrogen bonded to a fluorine, oxygen, and nitrogen? Because if I do, I'm going to assign the attractive force as hydrogen bonding. If I don't, then I'm just going to assign it as a dipole-dipole. If you determine that the molecule, the Lewis structure I give you, is nonpolar, then the attractive force is going to be a dispersion force. So melting points and attractive forces. So the melting points of compounds are related to the strength of the attractive force between the molecules or compounds. So that should kind of make sense. If this is a water molecule and this is a water molecule, and they are held together by hydrogen bonds, which are relatively strong, if I wanted to, so say, let's start off with ice. I've got an ice cube. So I've got my water molecules held together in this crystal, well, I don't really want to call it that, but they're held together in a fixed position. That's the word I'm looking for, because they're a solid. I have to put in a lot of energy to turn that solid to melt it into liquid, to where now my water molecules can roll around each other like they do in the liquid state. Okay, so you have to put in more energy to melt something that has stronger attractive forces. If it has a very weak attractive force like dispersion, you don't have to put in much energy to break that interaction, the attraction holding them together. So the melting points are low due to weak forces such as dispersion forces. So if your molecule has dispersion forces, expect a low melting point. Expect a high melting point if you have a strong attractive force like hydrogen bonding. And your melting points are highest in ionic compounds due to the very strong attractive force between the ions. Which is why when I told you to memorize the just some of those properties of ionic compounds, that one of the bullets is that they tend to be solids at room temperature. That's because they have a very high melting point because this attractive force is so strong. Here are some melting points of just some substances to look at. Magnesium fluoride and sodium chloride, they're both ionic because I have a metal to a nonmetal, and notice their melting points are really high. Then I'm showing you some hydrogen bonding here because I see a hydrogen bonded to an oxygen and a hydrogen bonded to a nitrogen. And both of those are, well, they're lower than ionic, but you can see that they're higher than your dispersion, which are higher than your dipole, which is higher than your dispersion. So basically I want you to see that the melting points are increasing as you go from dispersion to dipole-dipole to hydrogen bonding to ionic. So I have 2 slides here for you which are learning checks, so pause the video, come back, see if you can get it right. Identify the main type of attractive force that is present in liquids of the following compounds. And here are the 4 forces. I want you to tell me whether it's ionic bonding, dipole-dipole, hydrogen, or just dispersion forces. So the first thing you want to do is decide, is my molecule polar or nonpolar? Actually, that's not true. The first thing I would do is see if any of them are ionic, because that's the quickest to see. So this is a nonmetal to a nonmetal, nonmetal to a nonmetal. Oh, here we go. Here's potassium. Potassium's a metal. It's on the left side of the periodic table. So this one I'm going to say has an ionic bond. They're usually the easiest to spot, metal to a nonmetal. A, B, and D are all nonmetals, so I have to decide whether the molecule is polar or not. Well, in all 3 of these situations, I just have 2 atoms. So to determine if the molecule is polar, I have to first decide if the bonds are polar. Well, hydrogen and chloride, the bond is polar. This is a polar bond. So the molecule is polar. So once you decide the molecule is polar, that's going to limit us down to dipole, and hydrogen bonds. So we have to rule out hydrogen bonding. So my hydrogen here, is it bonded to an oxygen, fluorine, or nitrogen? No. So we're just going to say this is a dipole. Dipole. Okay, focusing on bromine, the electronegativity values are the same, so this is a nonpolar bond, which is going to lead me to a nonpolar molecule. And once you decide that the molecule is nonpolar, then you know it's dispersion. So that's a dispersion force. Hydrogen fluoride, if I subtracted the electronegativity values, it would fall between 0.4 and 1.7. Sorry, 0.5 and 1.7. So we would decide that's a polar covalent bond, which means the molecule is going to be polar. Once again, once you decide it's polar, we have to decide between dipole or hydrogen bonding. Do I see hydrogen bonded to fluorine, oxygen, or nitrogen? Yes. So this one is going to have a hydrogen bond. Hydrogen bonds are often abbreviated just as H bonds. That's another way of just symbolizing the hydrogen bonds. Okay, here's another one. Identify the strongest attractive forces that are present in the following molecules. So, once again, decide whether the molecule is ionic, and I don't have any ionic ones in here. So once you've ruled out ionic, then think about whether they're polar or nonpolar. So my first Lewis structure here, this is a nonpolar molecule. So I'm just going to go through real quickly and assign the polarity. So this one's nonpolar because everything around my carbon's identical. This one right here is polar because everything around my nitrogen is not identical because I have these lone pair electrons here. I look at the third structure, it's also going to be polar because if I circled all four things around my carbon, they're not identical. And this one here has got two central atoms. And I hope you can just kind of see that it's not a symmetrical molecule. That my oxygen here, if I circled the four things around my oxygen, it's not going to be identical, or the four things around my carbon are not going to be identical. So this is also a polar molecule. Okay, so the first one's real easy to decide what the force is because it's nonpolar. If it's nonpolar, it's going to have dispersion forces. Okay, polar is a little bit more complicated. I have to decide between hydrogen bonding or dipole. So I'm going to look for the hydrogen bonding first. Do I see hydrogen bonded to, let me write that up here. Do I see a hydrogen directly bonded to a fluorine, or directly bonded to an oxygen, or directly bonded to a nitrogen? So right here, yes, I have a hydrogen directly bonded to a nitrogen. So this one is going to have H bonds. Here, this one's a little tricky because I have hydrogen and I have fluorine. And so I get a lot of students who say, well, Bernadette, I have the hydrogen. You told me if it has hydrogen and fluorine in it. Well, I said the hydrogen has to be directly bonded to the fluorine. And here, my hydrogen is bonded to the carbon and my fluorine is bonded to the carbon. So this is just going to be a dipole. It does not meet the criteria of being a hydrogen bond. Dipole. Okay, focusing on this one, do we see hydrogen bonded directly to fluorine, oxygen, or nitrogen? And we do, so this is hydrogen bonded. All right, one more. Which of the following molecules can hydrogen bond? So I'm trying to trick you here once again, where I want to double check that you are looking for a hydrogen directly bonded to the nitrogen, oxygen, or fluorine. So this one we're going to throw off right off the bat because it doesn't even have nitrogen, oxygen, or fluorine. This one does have a fluorine and hydrogen, but they're not directly bonded to each other. I'm going to cross that one off. This one does hydrogen bond because there's the hydrogen directly bonded to a nitrogen. This one can hydrogen bond because there's my direct link. This one is another tricky one. I see hydrogen and I see oxygen, but the hydrogens are not directly bonded to the oxygen. So that one cannot hydrogen bond. So focusing a little bit more on hydrogen bonding in water, what does an understanding of what happens when water boils tell us about the relative strength of hydrogen bonds compared to covalent bonding? So I sometimes get some students who think that when you are boiling water, that they know that when you've got water, it is H2O. It's two hydrogens bonded to one oxygen. But every once in a while I get some students who think that when you boil it, what you're actually doing, because you can see the vapor coming off the gas, And students sometimes think that the gas that's coming off is actually hydrogen and oxygen gas. And that's not true. Okay, when you're boiling water, that is not enough energy to break the covalent bonds between the H2O molecules. What's happening is you're breaking the hydrogen bonding. So let me pull up this picture here. Be prepared. I might ask you to draw for me two molecules and show me how they hydrogen bond. So what you'd want to do is you would want to rotate the molecules so that a partial positive end is close to a partial negative end. So that's what I've done here. I've got my water molecule, and the partial positive hydrogen is being attracted to the oxygen on the other one. So I always need a hydrogen on one molecule, hydrogen bonded to either an oxygen, fluorine, or nitrogen on a neighboring molecule. So this right here is the hydrogen bond. And the question I'm asking you, so let me get my other pen. The question I want to know is, what is stronger, this hydrogen bond or the covalent bonds within my water molecule? Okay? And what I want you to see is that when you boil water, what you're breaking is you're breaking the hydrogen bond. And the gas that's coming off is actually just water vapor. The H2O stays bonded, covalently bonded together. So that should kind of indicate that a hydrogen bond is weaker than the covalent bond, because you can put in enough energy when you're boiling to break the molecules apart from each other. So now they're gas and there's lots of empty space between your H2O molecules, but it's not enough energy to break the covalent bond and actually make hydrogen and oxygen. Hydrogen bonding and water properties. So it turns out that the fact that water can hydrogen bond so strongly plays a big role in some of the unique properties we see of water. So I'm going to, when you're done watching this video, I have a CD. I'm going to put a video, for you to watch about some of these properties a little bit more in detail. So make sure you watch that video right after you watch this one, while you have this fresh in your mind. So the fact water can hydrogen bond plays a big role in how water reaches the top of trees. So you might wonder, how is it that water makes it from the roots all the way up to the top of the tree, defying gravity? And hydrogen bonding plays a big role in that. It plays a big role in why water has such a high surface tension, why water has such a high specific heat. It takes a lot of energy to raise the temperature of water. Water is able to store a lot of heat inside of it, and that is mainly because of the hydrogen bonding. Water has a very unusually high boiling point for such a small, light molecule, and it has some unique freezing and density properties that I want to show you on the video. It also, the hydrogen bonding plays a big role in why things can be cooled down by when water evaporates. Okay, so make sure you watch the video there. The high heat capacity or specific heat of water is sometimes utilized by people who grow plants to keep them warm when the weather is cold. So what you do is you fill up some milk jugs with water and you place them in between your plants about 2 to 3 feet. And what happens is during the day that the water jugs warm up, so they trap the energy from the sun inside the water in these jugs. And then at night you put over some sort of a covering that then, as the air cools down, the water inside the jug that has trapped so much heat, because it has a high specific heat, then that energy will slowly leave the water jugs. So the air will drop pretty quickly in temperature, but the water jugs are going to release all that energy they've stored from the sun and help keep your plants warm through the night. That's kind of cool. So make sure you watch the video now on unique properties of water.